Okay, how's the sound on this thing? All right, all good? So let's play Doom. So look at that, sound works and everything. Let's start the game. Actually, before we start the game, I'm going to just let's record. That's the pit. So let's record that. It's loud, isn't it? Wow, right. Okay, so that's now recording. I'm not really a gamer, but hopefully I'm not going to humiliate myself. I practiced a bit. Here's some bad guys. Zombies, I think. All right. So I'm going to stop about here. So if I come back, let's Control C. So now I've stopped the recording. Actually, it's really loud. Let's quit the whole thing. Right. So whew,
Might be the
that
first time I've ever heard that.
That was actually stressful. Right. So why was I doing that? Well, I don't know anything about the Doom source code. Well, I know one thing about the Doom source code, and I'm going to show how you can navigate a completely unfamiliar, medium-level complexity code base using time travel. So this is the recording that we generated. So the recording's kind of, you can think of it a bit like a core file, except for rather than a state just at the end, it contains all of the states of the program. So we're going to load that up.
Is this basically
let's go to the end.
Same tech as RR?
No, it's completely different implementation. Wow. There are some similarities with the implementation, and I'm going to get into all the details shortly. Good. So I've gone to the end of my recording, and so now I'm going to. So the only thing I know about this program, sort of cheating, is there's a thing called iVideo buffer, which is a 320 by 200 pixel, one character per pixel, screen buffer. So let's have a look at what that is. This is the screen buffer at the end of my recordings. That's the point I stopped it. Not the point I exited the game, but the point that I shut down the recording. So if I give this, so this is going to just show me what that screen buffer looked like at that time. Let's just zoom in a little bit. So here we are, that's when I stopped. So I've killed these two zombies. Now what I want to do is go back in my program execution to the point in time when those zombies got shot, or at least one of them got shot. So actually, we're talking, it's the title of the talk is how time travel debuggers work, and we talk about these things called debuggers. What we call debuggers aren't really debuggers. Like a debugger would be some kind of Gen AI thing that fixed your code for you. They are code understanding, program comprehension tools. And so they're very useful for trying to debug some horrible, nasty issue, but they're also just useful for understanding the code, right? And just, if you ever have to work in a big complex code base that you didn't write, and perhaps the person who did write it isn't even working in the team or the company anymore, what did it all do? So, what am I doing here? Yeah, so let's pick this dead guy here. So there's a bunch of blood. So I can see my pixels here down in the bottom in the middle of the screen, 179118. 179118. So I can look at that. So if I go plus, so it's a 320 row major array. So I want to see, when did that pixel change, right? So I can do this last command. Last, it's kind of like putting a watch point and running backwards. It's going to go to the point in the recording when that pixel got updated.
Yeah. iVideo buffer is a symbol of a global
Yeah,
symbol.
it's just a global symbol in the, that's the one thing I know about this program. So let's do, actually, I haven't got enough pixels really to do 2 mode. Let's do it in. So here's the backtrace at this point in time when that pixel got updated. Here's a thing called draw sprite. So that looks kind of interesting. So I want to go back to when that zombie got shot. So draw sprite. So, okay, so I've got this line here, and it's got some X and Y coordinates. So when did that sprite move? Like when it got shot, that's when it would have, fallen down. So let's go to when that sprite moved. I mean, they probably look like.
So RF.
Yeah.
What's the RF command?
Oh, I'm sorry. That's reverse finish. So that's like popping up the call stack one frame, but we're actually rewinding the program state.
So wait, stop. So go back to where it was called.
Go back to the caller. Yeah, go to the call site of the current function. Yeah, so here we're projecting this sprite. There's a parameter called thing. And if I look here, yeah, there's a thing, a member there called health. That's looking like an unhealthy zombie. So let's see when that changed, because the point that health changed, that's probably when it got shot, right? So we can do that again. We go back in time. So here we are. So it was -5. Now I've gone back to when it's 10. So that's the point. Should be the point and when it got shot. So let's have another look at the video buffer there. And yeah, there we are. Looks much more healthy. So cool, eh? So I just navigated through big pile of code, no idea what it all does, but I can see, I can ask questions about the code. So
when you asked about that thing changed, it was figuring out an address of a word in memory and then figured when that word in memory changed.
When did that change? What was the line of code that executed that changed that piece of memory? Yeah, any other questions on what we just saw? In that case.
So the last,
yeah.
if you call us again, it can go
yeah.
to the previous.
So you can keep sort of pulling that thread all the way back to kind of the ultimate source of that data if you want.
It's like a watch point, like you.
It is like, so that's another, I could have just set a watch point and then done a reverse continue, and it would have kind of done the same, but last is just a little bit more convenient. But yeah, I'm not really here to get into minutiae of the features. I want to get in and like how, this is not how to use it, this is a how are they implemented kind of talk. But that's basically the idea, yeah. That was fun. Well, let's get back, now time to get serious. Hang on, let me turn this on. Let's get to work. So yeah, I think this is important because most programmers spend most of their time debugging, right? Never works first time. I think how many lines of code do you think you can write and have it just work? I think for me, it's like 10 maybe, if it's real code. How many lines of code can you change and have it work first time in a complex code base? That averages to less than 1, right? So it's like programming is about debugging. It's getting the thing to work. Brian Kernighan put it better than I can, right? You might probably know this quote, it's quite famous. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? Now, very witty. And I think what he's getting at really is keep it simple. You're not quite as smart as you think you are. But I think there's a sort of corollary to this, which is that debuggability becomes the limiting factor on how good our code can be. Like for whatever your definition of good is, like whether it's how fast it runs or how small it is or how quickly you can write it, whatever your definition of good is, make it twice as debuggable, you'll make it twice as good. All right, audience participation time, not nearly as complicated as Michael's talk yesterday, you'll be glad to know. Much, much easier question. Cats or dogs? I want to show of hands, no on the fence, you have to make a call. Who prefers cats? And who prefers dogs? Just about half of you are wrong. There you go. So the point of this is I want to get you off the fence, right? You're going to have to make a decision. And now I'm going to ask something much more serious. Printf or debugger, right? I know it depends, and you can't. Right, you've got to get off the fence, and you've got to make a choice. So show of hands for printf, and show of hands for debugger. Ooh, kind of half and half. This time, you're all kind of right and all kind of wrong.
It depends, right? Like,
I know it depends, yeah. I mean, of course it depends, and that's why I did the cats or dogs thing, right? But you said that, you say it depends, but actually it's a lot of, it comes up every so often. It came up recently on social media, people getting very passionate about, oh, you should always use the debugger. No, debuggers suck, you should use printf. And it's like, of course it depends. But it depends largely because, yeah, they both suck, right? So you probably remember this XKCD cartoon was quite famous back in the day. They're slacking off because their code's compiling. Why is it compiling? Probably because they added a printf, right? I'd love to know what percentage of builds, not if it's like in the CI, but a manually triggered build, are because someone's added a printf and they want to compile that in. I reckon that's going to be quite a high percentage. Debuggers suck. Well, actually not for this reason. So this slightly less well-known cartoon, I quite like it, like the way, so step, 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 oh, gone too far. His future him is kind of reaching back in to kill past him, which I quite like. But that's just, I mean, that sucks. And it's one of the things that time travel debugging means that it doesn't happen anymore, but that's not really the problem, right? The problem is debugging, or just trying to understand how does code hang together, how did that happen? That's what you're thinking, trying to figure out what happened, right? Past tense. Not how did that happen? Not how did that happen? But I had expectations about what my code was going to do, and realities diverged from those expectations. And so the process of debugging, which actually is the root cause analysis of like what the hell happened, is to work out where did reality diverge from my expectations, right? Or probably a bit more like that. But this is a hard problem, right? A lot of the time. Computers doing billions of things every second, might be millions of lines of code. And so I'm sort of doing this jigsaw puzzle, running it again and again, getting clues, or maybe it's like trying to solve the murder mystery. And sometimes it feels more like that. But ultimately, hopefully, the last kind of clue falls into place and I understand what happened. And one of the things that makes bugs, well, I said hard to fix. I should have said makes bugs hard to diagnose, to root cause, is the time between the bug itself and you noticing, right? If there's like a segv because you didn't check a pointer to null and the pointer could legitimately be null, nice and easy. Worst case is always bad results. It didn't crash, it ran to the end, I didn't like the outputs. And it's also why assertions are really good, because they narrow that window, right? The other thing that determines how hard they are is how deterministic are they? Do they fail in the same way every time you run it? If so, I can just keep adding printfs. It might not be efficient, but I'll get there in the end. But if not, if it's non-deterministic, then it's like I'm doing the jigsaw puzzle, and every piece for the jigsaw puzzle is for a different jigsaw puzzle, right? And of course, when you're up in the right-hand corner, life gets really hard. And everyone's favorite is when we get the Heisenbugs, right? You add a printf, or you attach the debugger, and the program behavior changes enough that you can't get to the bottom of it. So printf logging is good at telling you what happened. It gives you a story of the program's execution, past tense. But it gives you just like little crumbs, little breadcrumbs of what happened, tiny bits of information compared to everything that's really happening. And I better think, if I can think in advance about what printf I need, probably didn't make the bug in the first place. Whereas the debugger lets you query anything. Like when I showed that little demo, I could look at the sprite x1 value, and you can just, without changing the program, I can see anything about the program state. And time travel gives you best of both worlds. Right. That's kind of the first of my 2 soapboxes today. The next is to come. Let's get into details about how do we do this magic. Oh, there's time travel. By the way, yeah, just in case it's not clear. So I use this picture for time travel partly because I think it's cool, but also unlike the kind of more modern sci-fi time travel things where they tend to go back in time and change history, we're not talking about that here, right? We're not talking about changing history. We're talking about being an observer, like the H.G. Wells time traveler was. I think this is an idea whose time has come, right? There are now numerous good, effective time travel debug solutions that scale and work for real, which is relatively recent. There are papers on time travel debuggers or replay debuggers or reverse debuggers or whatever you have various names, going back like to the 1970s, right? And countless PhD projects. I mean, I've lost count. I mean, I've spoken to dozens and dozens of people who've said, "Oh yeah, I tried to make one of those." But it's only in the last few years with these kinds of technologies that we've had things that really work for real, right? Work at scale, where you really need them, where you have millions of lines of code. Maybe you've got, many, many gigabytes, maybe terabytes of working set. Maybe they run for hours, maybe they run for days. And we can now time travel debug programs at that scale. right? Which is no mean feat when you consider what's going on. I'm only going to cover very briefly the embedded case. So these things, the Lauterbach Trace32 and the Greenhills Time Machine, these are hardware-based things. You need if you're lucky enough to have, well, one of these boxes and what do they call it? The trace macro cell on your embedded CPU and a JTAG you can plug it into, then you can do these in the hardware and they work really well. They're completely different kettle of fish, so I'm not going to talk about them anymore. More interested in the software implementations. So they're actually these are the main ones for C++. So there's undo, which I just showed you at the beginning. There's RR, which was just mentioned. That came out of Mozilla. RR stands for record and replay, and that's open source and works really well where it works. It's very good. I said GDB-ish, right? So GDB has had inbuilt time travel capability for some time, but it doesn't really work. Like, it's not real. Well, it can be useful in certain niche cases. I know some security researchers use it just to...
compatible with threads, right?
It is, no, it works with threads.
Every time I ever tried it, so I can't do this.
Oh, right.
Yeah.
But what it won't work, because if your CPU is like less than 10 years old, it'll probably get upset because it will see an instruction it doesn't. So I sort of mention it because it's there. Seems to be better known. People seem to know about it more than RR actually, which always surprises me. I'm actually always surprised how little RR is talked about and used, because yeah, it's good, it's free, it's there. Yeah, I guess I don't know. People are creatures of habit. So who here has used time travel debugging of any kind? Okay, about sort of half. And so the other half, come on, like at least try. Anyone tried and failed? I mean, you mentioned GDB, but we're not really counting GDB. Anyone tried one of these others and failed? No. See?
I don't actually debug that much. I mean,
Right.
if it compiles, it works.
You laugh, but there are times that's absolutely true. Once it compiles,
Yeah.
that's what Rust is for.
It's like,
Yeah, let's not go there.
It doesn't work, but you can see just from what it did, what's wrong.
Well, anyway, I encourage everyone, depending on what platform you are, depending on what kind of things you need, go try RR, go download an eval of us, go and use the Windows time travel debugger. You should at least try it, right? That's really my mission here. There's lots for not just C++. I know this is a C++ conference, but other languages do exist. Does replay.io have a cool thing for JavaScript for web developers, specifically for React, but works more generally than that. There's stuff on .NET. Visual Studio itself has some capability, and there's a thing called RevDebug. RR works on Rust and Go. Undo works on those and Java. Python is kind of, I said undo asterisk because it's not really a first-class citizen, but you can now time travel debug Python programs. PyPy, they were working on it. They seem to have stopped. So I'm not really up to date exactly why. I'll get into, but I've got a hunch, which I'll get to. So this was the first one that I saw. This is a thing called the Omniscient Debugger. You can actually see at the top there. This is from 2006. And I don't know exactly when it was when I saw this, but sometime around this point. And my mind was blown. I could immediately see the promise of this. Now, this is a Java thing, and it's just what they did is just instrument all the memory accesses at the JVM layer. So it's unfair to call it a toy, but it didn't sort of scale, and obviously it certainly wouldn't work with C++ or any compiled code. But it got me thinking that looks really interesting. But how do you design this, right? How do we actually make this work? So the program is destroying information all the time when it runs, right? So when I was running Doom or whatever I'm doing, like it's just destroying, the processor is destroying information. Actually, there's some interesting research on reversible logic to make CPUs actually be reversible at the hardware level, because it turns out that saves energy, at least in theory, because there's some kind of E equals MC squared equivalent for information. So if you're destroying information, that consumes energy, and they make these reversible. It's quite interesting, but it's kind of out there, right? You can't nowhere near being able to buy these things. So on a regular commodity piece of hardware, how are we going to remember all that state? So it's like, sometimes say it's like having that recording. I said it's like having a core file. It's like having a core file for every single instruction that executed. That's a lot of core files. So obviously we're not going to do that, right? That's just clearly not going to be the thing. But maybe the next thing you think is, well, maybe what we'll do is just store these kind of keyframes, and then what we'll do is we'll store all the changes, every change that happens. Even that turns out to be difficult. So yeah, what happened is what we're trying to do here. If we're going to say this in a slightly more kind of computer science-y way, what was the previous state, or what were the previous states of my program? And there's kind of two ways I can do this. So yeah, I can save it. I can save at least everything that changes, the deltas, right? If I'm going to have an instruction level, the deltas between each instruction, that's a lot. That's a lot of state. The computer's doing billions of things every second. Every instruction has to change at least some state, otherwise it's live locked. So that's like 16 bytes every nanosecond. That's just a lot of data, and it's going to go very slow. So it's not really a good option. Better option is to recompute it. But as I just said, computers don't really run backwards. So how are we going to do that? Well, in fact, some statements are reversible. If I just run that statement and I know that A and A is 42, then obviously its previous value was 41. But that statement's not reversible. After I've executed that, I've got no idea what A was previously, right? In fact, even the first one's not repeatable. Let's say I'm in the debugger and I'm at this line here. What was the previous line to execute? Like maybe it was the one right above it, but maybe there was a goto. Maybe I smashed my stack and returned off the function and ended up somewhere random. This is one of the things that makes this kind of hard, is they are debuggers. They are kind of intended to be used on buggy programs, so all bets are off. So you first thought, well, can we do some sort of static analysis so that we can kind of figure out what paths are possible through that? Well, no, you can't, right? At least not with, not with C or C++ or something. And even in the general case. So we don't even know what the previous line was. But what if we could rerun it? And that's, in fact, what we do. And that's what pretty much all of these things do. They re-execute the program. So if you think of, imagine our program state to be a number. Right? All of the memory and all the registers and everything, great big, it's a big number, but it's still a number. The biggest number is actually even bigger than that. And we've got some function that we can apply to that state and get the next state. Well, that's what the CPU does, right? So we can rerun the program, and given the same starting state and feeding exactly the same inputs, it will do the same thing. So if I've been, like, if I run 1,000 instructions and I want to go back one, I'm going to start from the beginning and run 999. And we can see this. So so here's the Doom demo I showed earlier, and here's a bunch of these snapshots. You don't actually need the snapshots. They're just a kind of optimization. We could replay from the beginning every time, but that would get kind of tedious. And I'm currently at, let's...
Are the snapshots stored as deltas from the previous snapshot?
Effectively, yes.
Okay.
Yeah, they're copy on write.
Okay.
So effectively they're deltas, yeah. So yeah, so here I am at this snapshot 16, which is at this time 687 million. These are kind of basic block-ish things. So if I've got the time down here at the left, actually. So if I reverse step, we may or may not go back. We didn't go back one that time. OK, so now we've gone back from basic block 580 to number 579. And if I look at the snapshots, I can see, here we are, as you can see, this has changed, right? So what it did is pick up a snapshot from here and run it forward to just before where it was. Feeding in the same set of inputs. So computers are completely deterministic, except when they're not, right? So when I replay it, what happens if I get time of day, right? When I program around enrichment, and Doom, when I was playing Doom, get time of day would return the time 11:02. When I'm replaying it now, get time of day would return 11:25. So when I played Doom originally, we will have stored in the event log all these events. I'm not going to wait for them to all scroll by, but you can see these are all the non-deterministic things that it did. Oh, look at that. That wasn't intentional. There's a clock get time right there. Okay, so we've got different things here. We've got some system calls. We've got some shared memory fix-ups. So we've got these different things that are kind of unpredictable. Things that mean there is no function that exists that given x, I can produce x prime.
Well, if you're writing to the file system, then
Yeah.
you have to be snapshotting your file system too.
So when I was playing Doom at the beginning, that was going for real. That was doing all the system calls, and we could see the pictures and hear the sounds and everything.
Yeah.
When I was replaying inside, I'll show you, right? It's not actually touching the outside system at all. So this is I can go right back to the beginning. I can replay the whole thing. There's no sounds, there's no video. It's kind of isolated from all the system calls are kind of stubbed out.
Okay.
And any reads are contained, when he reads in the file system that it did, are contained in that event log. So it will get the same result.
It's not reading the file system, it's reading
Not when I replay.
from the
Yeah.
record.
Yeah.
Okay.
Yes, question.
It seemed like you were playing Doom like in real time. What's the
Yeah.
slowdown when you install?
So different technologies have different kind of trade-offs on that. The thing I was showing is, I mean, actually I was surprised when I looked at this that, actually there's a lot of threads here. So these are all the threads that get created at the beginning of time. But single-threaded slowdown will be from, depending on the thing, I mean, on this one, sort of between 1.5 to 5x kind of range. Multi-threaded slowdown will get worse. Very I/O intensive, well, it will depend. Some I/O intensive programs run with almost no slowdown because all the time is blocked in I/O. Others are just churning through huge amounts of I/O and there's lots of processing to do. But anyway, that's a long-winded way of saying 2x to 5x, maybe 10x is the kind of slowdown you should expect. So what's unpredictable, right? So give me some, so we'd already said system calls, so I think that's the first one on there. What else?
CPU ID and RD ran and other instructions.
Yeah. Well, you're kind of cheating because you've actually made one of these. So yes.
Scheduling of threads.
Yes, right. Threads, that's a big one. We'll talk about that in a bit. Unpredictable instructions, RDTSC and co. System calls. There's two more. Things that you just can't predict when you rerun the program.
Volatile memory.
Yes, volatile memory. So we saw in the event log there were some shared memory fix-ups. So most memory holds a property that when I read from it, I read back what I most recently wrote. Otherwise, I'm probably going to send my memory back for a refund, right? But except not if it's shared with another process or with the kernel or with the device doing DMA into it, right? So sometimes memory is unpredictable. And there's one more.
User input?
Yeah, so user input would probably be system calls.
Oh, okay.
It's the one that actually...
UB.
Yeah.
Sorry?
UB.
No. So weirdly, undefined behavior is predictable when you're replaying, right? Because it's just instructions, and unless you happen to do something weird with the system call.
x86 doesn't have.
Yeah. Right, but yeah, at the machine level, yeah, we're talking about instructions here.
The initial state is not predictable.
That's true, yes. That wasn't the fifth one I was looking for. Yeah, you're right, you need the initial state. Fifth one I was looking for was signals. Asynchronous signals. So we need all of these. We need to capture all these, but that's a tiny fraction. Although there's a lot of it, and I showed you the event log for Doom, and lots was scrolling by. It's a really small fraction of what the program was doing, right? It's like 99.99% of it is just like add these two numbers together, add the same two numbers together, better get the same result, right? Except actually not. In fact, I think if we're going to be pedantic, system calls are just an example of non-deterministic machine instructions. Right, so there's a syscall or int80 or whatever, or svc0 if you're on ARM or whatever it is. Those instructions they mean I can't predict the results based on the current state of the program. If I could predict the result of a system call based on the current state of the program, then it probably oughtn't to be a system call. It ought to be a library function, right? So yeah, depending how you count, I mean, it's a bit pedantic, I think. It's 4 or 5, depending on you count, maybe 3. Anyway, so here's some code. And all of this is completely deterministic. If I run it with the same state, Assuming there's no threads getting in the way or anything like that, it's going to give me the same result. This one is not. So I've got to record the results of what that does and replay them. So that's the first design decision. Are we going to store things every change as they run, or am I going to re-execute? And re-execute is the clear winner here, right? It's all the workable systems, TTT from Microsoft, undo, RR, replay.io, they all work through re-execution. Turns out to be the best way. In fact, what you're effectively doing is like is a really amazingly effective compression technique, right? Okay, second design decision. At what boundary or what level are we going to record things? Am I going to record a whole process, or maybe threads or functions? If it's Java or JavaScript, maybe I can make my JVM be reversible. And this is actually what the PyPy people are trying to do. Or maybe you can do it at a virtual machine, like a KVM or VMware virtual machine level. The only ones that really work is process and virtual machine, because there's replaying, as you said, there's just these 5 sources of non-determinism, and just have to capture all those and replay them and everything's good. I mean, it's harder than it sounds, right? It's quite fiddly. You have to get it like perfect, because ironically, a re-execution based time travel debugger is really hard to debug. It's like, well, I've got more slides than I thought. It's right up there, right? Because you tend to, if you're replaying and you slightly diverge from the original execution, you tend not to notice for a long time. And it's like by definition non-deterministic, right? Because I didn't get all my non-determinism. So I wouldn't have gone all the way back if I'd realized quite how many slides. Yeah, so re-execution is the winner. So yeah, but I can, at the process level or at the virtual machine level, it's just about tractable. I have a well-defined, kind of guaranteed by the hardware interface. I know nothing, my Linux process, if that memory is not shared, if that memory is private, I know nothing else, and I've not got some asynchronous system call writing to it, I know nothing's going to come from the outside and just change it. If I'm doing it at the kind of, if I'm modifying my JVM, say, it's really hard to know exactly what's going to happen. It's going to really depend on the JVM internals, and just becomes not practical. So I mentioned replay.io. They surprisingly do it at the process level. So they provide time travel debug for the web developer, and the web developer can step their JavaScript code back and forward, just like I was doing in the demo. They do that by giving you a custom browser. They forked Firefox, and more recently Chrome, and they're rewinding the browser state to like just that like point in the JavaScript code, because they originally tried to do it by messing about with V8, and it just wasn't practical. So that's where they ended up. So yeah.
Does the Docker image fall into the VM category or not?
I would no. I would say Docker's not going to fall into the VM category, because so you have processes within. I mean, Docker's really just like a group of processes, right? Yeah. So that's just a bunch of processes. So we're recording at the process level. So libc and all of libc, for example, is inside that Doom recording that I just showed you. It's all there. It's everything that's inside that process. Now I might record multiple processes. Just showed you Doom was one process, but I might have many processes. I might have many processes across many machines. That's fine. I can record all of them independently, and I can even stitch them together at replay time. But the kind of unit of recording is the process or the VM. There are some people doing stuff at the VM level, and that also works. It's depending, depends what you're trying to do, usually less practical. Most of the time, I don't want to have to create a VM in order to like debug my thing. I want to be at the process level. Also, yeah, I might have distributed across many nodes, and we don't yet have sort of distributed single system image virtualization stuff. So process or VM, mainly process. So another clear winner for design decision. Number 2, re-execution at the process boundary. Now, with the coming design decisions, there are no clear winners. We're into the usual thing. You get a bunch of trade-offs, and it depends kind of what you want. So yeah, how to track time. So time, I've been talking for 36 minutes about time travel, debugging, and I haven't even mentioned time. So yeah, we better think about time. So yeah, time travel, right? Ooh, there's not actually this kind of weird, kind of relativity thing. It's much more boring. But I've got to track time. I've got to track my process execution time really precisely. Because, for example, if I am going to replay a SIG alarm that came in, I better replay it like at exactly that point, exactly that instruction. And it's not good enough actually to just at that instruction, because that's space and working about time. Programs are full of loops. Any program that doesn't have a loop in it is going to run, to the end, to termination in microseconds or whatever. So programs are just full of loops, and I'm re-executing the same instruction all the time, and I need to be able to replay that SIG alarm at exactly the right iteration of the loop. In fact, if I want to be able to step through code, then I also need to when I'm replaying, when I'm re-executing. So when I said before, I've done 1,000 instructions, I want to re-execute 999 in order to go back one. Well, yeah, that's a little bit more involved than it sounds, because, well, which one? Like, what do I mean by that instruction if I don't have a precise notion of time? Let me show C-line here. I've resized the pixels on this from plugging to the monitor. So let's see how well this, have I got enough screen real estate? Possibly not. Mind you, I could probably, so here I am in, let's restart that debug, see what happens here. Okay. I might have to, C-line has this really nice presentation mode, but it depends how many pixels you've got. Right, so let's just step forward. So I've got just this loop, right? And it's counting loop, and C-line is telling me how many times through I've been. I've got a breakpoint on the end here, so let's just run, let's continue that to the end. And I'm gonna go back line by line. And so I is 9, because that's the final iteration of that loop. I go back again, now I is 8. But so each time it has to re-execute to the right point in time, the correct number of iterations of that loop. So I can't do it with breakpoints, right? So I need this really precise measurement of time, and which is going to be some kind of equivalent of how many instructions have I executed. You can kind of, we have in undo, we use how many branches have I taken plus concatenated with what the program counter is. That gives me a unique notion of time. RR does something very similar. I think the Microsoft TTT is just how many instructions you've executed. Exactly. Yeah. So that's kind of, you need some way to do that, and it's not as easy as you might think. There's 2 ways to do it. You can JIT the code, so do a just-in-time binary retranslation of the code to like put little counters in and see how, to track progress that way. Or you can use hardware counters. So modern CPUs come with these performance counters. They're kind of meant for performance, but they can work here mostly. So with binary translation, we translate the program. This is how undo works. Similar story with TTD. This is in record time, right? So it's accessing the kernel. Replay time, there is no kernel access, as we spoke earlier. Yeah, so I can use the performance counters, and specifically, but there's some catches here. So they're not guaranteed by the CPU vendors to be completely precise. They are for performance, they're for benchmarking. So they kind of come with these caveats. It turns out in most modern CPUs, there are certain performance counters that are precise enough to do this. Specifically, the retired branches. So how many branches did it actually take? That seems to be reliable on modern most modern x86s, kind of on ARMs, but there are some caveats on, like with Graviton, for example. So particularly the ARM has this load exclusive, store exclusive instructions. So load lock, store conditional, basically, yeah. They call them LDX and Strex, but yeah. And they confuse the performance counters. They're not kind of, they're not kind of totally, if there's a retry on the store conditional, the performance counters are kind of off. There are other catches, but on modern x86 at least, yeah, they're good. And with those few caveats on ARM even, they're good enough to do this. And so now it's nice and fast because I'm not jitting. And it's a lot easier, much easier implementation to rely on this stuff. So this is what RR uses. And yeah, I mean, for a simple CPU-bound, single-threaded workload, really fast. Like the overheads are, in the like low digits %. And yeah, they don't have to have all this complicated JIT binary translation code. They don't have to deal with stuff like writable code, JITted code. That all just works. So lots of advantages to doing it that way. But there are advantages to the JIT side of the JIT. It's what undo does. It's what the Microsoft TTD does. And actually, replay.io does a kind of combination because it's a bit complicated. The nice thing about jitting, though, is it's an entirely software solution. So it basically works anywhere. So the performance counters often just aren't available. If you're running in a multi-tenant AWS machine, the performance counters are deliberately not exposed to you because there's worries about side channel attacks and the like. Now, if the perf counters are really as deterministic as they seem to be, then actually you can demonstrate that isn't a security risk. There is no side channel timing attack that's possible, but there are no guarantees that they really are. So yeah, I think it's pretty obvious why AWS and Azure and others don't want to make them available. A lot of virtual machines implementations just don't make them available as well. So they're often just not there. And with doing it with JIT binary translation, I've said works with anything asterisk. So because it's all software, you can kind of dig yourself out of any hole. You're not relying on the hardware to do some kind of non-guaranteed thing. And there are other things like particularly shared memory accesses, which there is the only hardware support for shared memory accesses would be to fault on every access to shared memory, and that would be horrifically slow. So JIT lets you do like more stuff. So you can work with more programs, makes it practical to attach. So I showed attaching to Doom at the beginning, so I can dynamically start and stop recording. And the other thing I said here is solid. So yeah, there's some nasty catches with perf counters. One of the things though, it's not just, I need not just a measurement of time, I need to be able to go to a particular time. So I can use my perf counters to say, yeah, I've done exactly 16 billion, 124 retired branches. Now when I'm replaying, I want to stop 1 unit earlier. How do I do that? Well, it turns out that the hardware also has this really neat stuff called PEBs, Precision Event something. Yeah, I can't remember. Anyway, and that lets you trigger an interrupt. PEBS, I think that's right. Yeah, yeah, precision event bullshit. I don't know. No, it's very cool. And so it lets you sort of program the chip. So after this many, when the performance counter hits this threshold or decrements down to 0, I think actually, isn't it? Generate an interrupt, so you can use that to get where you need to be. Except that's not actually super precise. So there's quite wide error margins in there. So what you have to do is you have to program that to stop quite a bit before where you really want to stop, and then like just step forward bit by bit to get to where you really need to be. And so it's kind of sketchy, right? the other thing you need to do is intercept syscalls. You could do that using ptrace. So you can get ptrace to stop when a system call is executed. But that's going to be kind of slow. Every time a system call is hit, we'll have a context switch back to ptracer, which will then do some stuff and then continue to resume the tracee. So RR doesn't do that. RR uses setcomp to kind of get control and so actually does a mini bit of jitting in a way. It does a bit of patching of the program to intercept those syscalls efficiently.
When you say JIT, you're talking about emulating the actual instructions of the program.
Yeah.
Software. One by one, or are you
so
inserting
what we really do is, we would take this basic block. We're working. They're not technically basic blocks, but let's call them basic blocks. Take this basic block, which ends with a syscall. That I can mostly just copy that directly to my sort of instrumentation cache, and then this is completely different, and I do all the magic that I need to do to handle this syscall. Except it's not quite so simple because here we've got a RIP relative access. So if I'm executing this from a different location, I need to patch that up as well, but detail, right?
But
so
you're actually letting the processor run those instructions.
It's running for real, yeah. I've just replaced the non-deterministic ones and actually the branches. So partly so I can count and partly so that I can not branch back to the original code. I've got to stay in my JITted code. So this is really nice. It lets us do all kinds of magic. The other thing you can't do with perf counters is these, we talked about, James mentioned the non-deterministic instructions, right? So you can actually configure the CPU to trap when there's an RDTSC, and RR does that, and that kind of works, although it's a bit slow. There are other instructions where you can't trap. There's instructions to generate random numbers. There are, and some of them like some of the flags can end up non-deterministic in certain conditions as saving out the what they call the X-save area, which is like all this kind of process-dependent state. Actually, quite a large number of instructions become non-deterministic, and you can't capture those. So if your program relies on those and does non-deterministic stuff with those, you kind of really need the JIT approach. So JIT, performance counters, pros and cons. Decision 4 is whether we're going to rely on memory determinism completely. So and this is the difference between, so undo and RR are quite similar here, and TTD is different. So with RR, well, undo is kind of in the middle of the two, actually. So with RR, it just assumes that all the memory is deterministic, right? And if your memory is shared with something else, it's not going to work. It's not quite true. So you can record an entire process tree. So if memory is shared between other processes in your process tree, RR can cope with that because it re-executes the whole process tree completely in lockstep, and so it's deterministic. But if the memory is shared with anything that isn't one of the processes that RR is recording, can't do it. At undo, let's do the TTD version, and James will correct me if I'm wrong, but my understanding is that every memory read is like, what you do is stash it away, and then the next time you read from that location, check, did it change since last time? And if it changed since last time, then I need to create some sort of event. And of course, most of the time, it won't have changed since last time, because most of the time you're reading what you just wrote to the stack. It's going to be completely deterministic, but maybe some syscall has blatted into it or something, or maybe something's DMA'd into it and it's changed. And so that is slower because I've got a certain amount of work to do. Every memory access, I've got to do all this work to see has it changed, and will potentially generate larger, actually sometimes quite significantly larger recordings. So with TTD, the recording is generally proportionate to how long the program has run for, right? With RR and with live recorder, with undo, it is not as simple as that. And some programs that are very compute bound can run for a really long time with very small event logs because not that much non-deterministic stuff happened. So the event log with undo and with RR is more proportionate to how much input did the program process when it was running. The other good thing about doing this, so you can deal with unknown syscalls. So again, RR and, well, again, undo is kind of in the middle of RR and TTD. So RR has to know what all of the system calls do. And it's not too bad. There's like, depending on how you count, there's about 400 or 500 different system calls on Linux. It's kind of painful, but it's all right. And they have well-defined semantics. So, read is going to read exactly this number of bytes to where I told it to, and it's not going to change any other memory. And there's an exception here with ioctl. So ioctl is like kind of all bets are off, but basically RR just needs to know about all the system calls. It knows about most of them. And for TTD, it's different. My understanding is that whereas Linux has a lot of system calls, maybe 500, Windows has thousands. Nobody, including people at Microsoft, know what they all do. And they can change because the ABI compatibility is at the Win32 layer. So they kind of TTD couldn't pull that trick. So it has to just say, yeah, well, memory might change and I need to check all of it. But it does have a really nice advantage that you can record multiple threads in parallel. So yeah, so that was a question that came up earlier. How do you deal with threads? And this is what both undo and RR will do, which, look, let's be honest, it's not great, but not nearly as bad as most people think it's going to be in practice. So threads are running in parallel. We're just going to serialize them all down. So one thread is running at a time. We will allow the OS to preemptively schedule new threads, right? So you can reproduce nearly all race conditions. The only race condition that won't reproduce with this trick is if you have a missing memory barrier. Those memory consistency things just kind of go away. So the memory kind of behaves nicely. But most people aren't working at the level of memory barriers. If you're just using pthread mutexes and whatever, you don't need to think about that. And then basically every other race condition will reproduce, actually often quicker. It's interesting how often just slowing down the program causes those race conditions to be more likely to bite. But yeah, if I've got 16, 32 threads, I'm going to have a kind of per thread slowdown. So whatever slowdown, I'm going to multiply that by 16 or 32. Well, if my program were perfectly parallel, right? But actually most programs aren't anything like that. So most people think, yeah, well, I've got 16 threads, I'm going to see 16 times slowdown. They don't see anything like it because their program isn't quite as parallel as they thought it would. And you also get complexities like when you're running on a single CPU core, that'll get overclocked, boosted, I think they call it. And so it slows down, but not as much as you might think. And it does reproduce all the race conditions. But clearly it's better to be able to record all of the things in parallel. And that's one of the real strengths of the TTD approach. So it's a bit more expensive in the event log it needs, but you can do this parallel record. There is.
What is the granularity of those circles there? Is that like the basic block?
No, it's just some non-specified unit of time.
Okay.
So yeah, actually in our default mode, we will thread switch only on basic block boundaries. So that will mean a lot of race conditions go away. But we have a thing called thread fuzzing, which will like aggressively schedule.
Because you actually do want to trigger all your race conditions.
Exactly. Yeah. Probably working on actually enabling some thread fuzzing by default. We're sort of experimenting with performance things. So it's a bit of a trade-off, like how quickly do you want the thing to record and how aggressively do you want it to schedule. But yeah, thread fuzzing is really cool, actually. It can, RR has a thing called chaos mode, similar kind of idea. One of the things you can do when you're jitting, though, is detect certain instructions that are like fishy locked prefix instruction that kind of looks like there's some kind of sharing going on here. So we'll pause that thread for a long time, let all the other threads do loads of work, and then resume it, see if it's okay. And the nice thing is, when you capture your race condition in your recording, it's easy, right? I mean, it's just
It's repeatable then.
it's totally repeatable, and you can just figure it out. Yeah, it's like it's just yeah.
Just figure it out.
You could, like, just honestly, I've had multiple people say, when I have a recording, I know I'm going to have the bug fixed that day. I'm happy to tell my boss it's going to be fixed that day. Which, if you go and tell your boss it's going to be fixed that day, actually you're pretty confident it's going to be fixed that hour, right? Yeah, as I said, undo sits kind of in between RR and TTD here. So we will assume that most memory is deterministic, but you can actually tell the Linux kernel is quite helpful here. It will tell you which maps are shared. If you look in, here in proc maps, it tells us here. So actually, all of these P's, there's no shared memory here, right? That's just because that cat, I guess, is the program that's running there. But if they are shared, we can know, okay, that memory shared, that might change. Oh, my animation, thought I'd fix that. So actually, right. So going to be really pedantic. There's now only 3 sources of non-determinism because these shared memory accesses are just reads, right? So some read instructions are non-deterministic, are unpredictable. So actually now I've just got 3. I've got some instructions I need to worry about. And so we can figure out these instructions at least sometime read from shared memory, so they need the extra stuff. Asynchronous events and thread switches. Maybe thread switches and asynchronous events are kind of the same thing as well. So really it's non-predictable instructions and asynchronous things. So just to recap, so we've got this question of what boundary to capture. So ODB, that's unfortunate acronym, but I'm going to spot the omniscient debugger. So that's the only one of these examples that doesn't capture at the process boundary. And it's the only one that's not kind of in serious use. Binary rewriting instrumentation, so it's a bit of a mix. So undo does it, RR doesn't, when debug, sorry, that's TTD, when debug does it, replay doesn't. All or some recording of memory, so just talked about that. One thing I haven't mentioned actually is separate record and replay phases. So the demo I showed you first with Doom was I took a recording and then I debugged that recording. And I could be debugging a recording that I took yesterday or last week, could be in a customer machine that I don't even have access to. Or can I just use an interactive debugger, which is what I did in the second demo I showed in C-Line when I was stepping back through that loop. That was just an interactive debugger. I don't necessarily have to take a recording and replay it separately. So it's nice to have the choice. And then parallel threaded recording. So those are kind of the design decisions and kind of the trade-offs that you get. Any questions? Yeah.
What are the compatibility limits between the machine you record on and the machine you replay on?
Yes. So that's another advantage to jitting is we can, again, it's just software, so you can do what you want. So we will, in undo, we will emulate instructions. So you might have instructions that don't exist that exist on the record machine, but don't exist on the replay machine. And we'll emulate some of those. It's not complete, but we'll emulate the ones that are kind of problematic. Yeah, when you don't have jitting, it's just not going to work. You're going to get a sigil when you're trying to use one of those instructions. And you have others that are, yeah, Xsave is unfortunate. That will just, depending on what CPU you're running on, will just like do a different thing. So you have to kind of deal with that as well. So sometimes they don't exist sometimes. But generally, the recordings are very portable. One of the nice things in undo recordings is we'll also fertile around if there's any debug info that looks relevant, suck that into the recording as well. So you've got everything. The only thing that's not in the recording is the source file, is the source code. Basically everything else is in there, even the program executables and stuff. So yeah, pretty portable. James.
Yeah, I was just going to say that on the Microsoft implementation, you don't even have to replay on the same architecture. Like you can make an portraits and replay on the.
Oh, can you? Oh, wow.
I was also I wanted to ask a question though. So you were showing the demo where you were just recording in the debugger and then running backwards. Can you then like run to the present and resume?
And keep going. Yeah, you can.
Cool.
Yeah. Yeah. Actually, that was a bigger design decision I didn't list, which I probably should have, because yeah, back when we started, I was adamant that like it has to just look and feel like a regular debugger, otherwise it's going to be really hard to get people to kind of change their habits. So I want it just attached, and it just needs to look exactly like GDB in terms of like your workflow. Honestly, if I was going to have my time again, I probably wouldn't do that, because it was a lot of work and continues to be a bit of a maintenance headache. Like, it's cool and people really like it, so we're not going to take it. We've done all the work, so we're not going to take it away. So having done it, I'm glad it's there. But yeah, that ability to like have the same session be sometimes recording and sometimes replaying gets just a lot of edge cases to deal with. So it's nice. It's a nice feature. People like it. You know, is it worth all the hours and hours that went into it and blood, sweat, and tears? I don't know.
And you can't go back in time.
All right. By the way, oh damn it. Okay, two things I was going to say. We're allowed one time travel joke per session, so we've just had it. And I forgot to do. I also have swag. Not very much, because like I'm really fussy about only taking hand luggage on the plane. But who would like to have a mug with loads of x86 assembly code on it that contains a bug? So this is a prize. I should have done this at the beginning. Sorry?
You got any mugs with ARM instructions?
No, I just got one mug. This is going to be a prize for the best question, which I did at the beginning. Also have some bottle openers, because they're small. Yeah, right.
This detecting race conditions, it's like this is a whole separate value proposition for these tools.
Mm-hmm.
Like, even if I'm not trying to debug, I'm going to want to do that. Does the usefulness of the different ones vary for that purpose?
Undo and RR is similar. So RR has a thing called chaos mode. Because we have the jitting, we can do a few tricks that RR can't, but they're kind of similar. So I'd say there are a lot of cases where, but basically it's really, it's none of them are guaranteed to work. So it's not like if you run with thread fuzzing, you've got like thumbs up. There are definitely no race conditions in your code. Well done. And there are times, it's rare, but there are times that you just cannot get the thing to reproduce. I've had that feedback from a couple of customers. So they love it. They completely depend on it. They can't. It's kind of a sign of. I take it as a compliment, as saying that like I really need to be able to reproduce my race condition in recording, otherwise I'm stuffed. And like they rely on being able to do it. But yeah, so reproducing a race you know about, but also finding races that you didn't know about, or maybe only your customers see, but you can't reproduce in test. Yeah. There's questions back here.
So do any of the what kind of things do you have to do to handle like jits running inside the thing you're doing?
Yeah, that's good fun. So you have to. The thing is, you have to invalidate. You've translated the code. You don't want to retranslate the code every time, so you kind of keep this cache of translated code, and then when it's written to you, you need to invalidate that cache. Cache invalidation being one of the two hard problems. You know that joke. So that's kind of tricky. What we do is some madness with the protection settings. So we'll detect that's happening, then we'll mark the memory read only, and then when the program tries to write to it, it'll trigger a fault, and then we know, okay, we need to update the caches. So that's the configuration option actually. So pathologically that can perform worse. If the thing is like write, then execute, then write, then execute. But most things don't do that. Most things kind of JIT. So when we have a Java solution, and it sort of comes back to the process boundary thing, right? So yeah, in the Java solution, when we first did that, it was like, well, there's a discussion on should we just throw away all our existing stuff and just change the JVM to be able to do this. And we didn't, partly, to be honest, because we already had all this stuff, right? And so didn't want to start again. But also because it gives you lots of, it actually performs better. And I talked about all that. And also you've got JNI stuff, it all just works. But yeah, that JITs, obviously. So we needed to make that high performance. We also have customers who, in the EDA industry, who do a lot of JITting. So yeah, that's kind of an important use case. It's fiddly. Yeah. I don't know if TTD has similar.
In the WinDBG implementation, they're just memory reads because you're just reading the instruction stream, to execute them, and so they detect, when they've changed.
When the I see. So your execution is also a memory read. Right. Yeah.
What is the business model that supports undo?
We provide really good software, and people pay us loads of money for it.
Okay.
Yeah, it's like, it's not cheap, right? So you can have, we sell a single floating license is kind of the entry level thing, and that's $7,900 a year. And we kind of, I don't want to get into a big business discussion, but it's kind of been an interesting journey because it turns out this is one of the things that got easier over the years. Back when we started, we've been at this for quite a few years now, and I have this line that programmers would treat tooling a bit like they treat sex, as if you have to pay for it, then that's kind of a shame,
Yeah.
That's kind of gone away, actually, on the tooling side. I don't mean the sex side. That's people are more open now to paying for tooling, but it still kind of goes into two camps. You get some people, so those who do are like, well, if the ROI is clear, if I'm going to make back way more money than I'm spending, then I'll buy it. So that's kind of who we focus on. But yeah, anyway, that's the business model. Chris.
I know that Undo has some support for time travel debugging for Python, where you're like recording the Python virtual machine. How exactly does that work? Out of curiosity? Like, obviously it's recording like anything else, but how do you actually kind of correlate Python source?
So when I listed Python, I put a little asterisk because it's not really it works, right? It's effective. People use it and they debug difficult Python issues with it. It's just not quite the seamless user experience that our other language support is. So, but yeah, it's relaxed. There's stuff in Python. Let me get this right. Python ships some GDB extensions for debugging Python programs. That's not a bit. So you can get, by loading these extensions into GDB, you can kind of get a meaningful backtrace, and we kind of build on that. And so, yeah, you can time travel to where you want to go. You can see a backtrace. You can't do things like, and that's not true now. I think you can. I think we made this work now. You can even do reverse next and things. So it actually works. It's kind of neat. It's just not kind of seamless. And so we've gone to a lot of effort to make that. When you reverse next, you are like definitely going to the preceding line. Very important that the debugger doesn't lie to you. But it's, so it's like, it works, people are using it, and you can just like download the stuff and use it. It's not nearly as well tested and battle hardened as our other stuff. Yeah.
Can you talk a little bit about the IDE integration? Is it been like consolidated, sort of like a language server model, and like how?
Yeah, that hasn't really helped, unfortunately. So there's this what do you call it, the LSP and the DAP. Yeah, that kind of works at a different level. So all these technologies, they're not. Well, I've said WinDBG here, but if you want the TTD bit of WinDBG, they're not about source level debugging, right? There are existing debuggers, whether it's GDB or LDB or WinDBG, that do that just fine. So they're provided, what they're about is reverse execution or time travel replay of a process. And then the debugger kind of attaches onto that. So the debugger adapter protocol is between the debugger and the IDE. And what we need is kind of between the debugger and the thing underneath, the process being in the world. So so that unfortunately kind of hasn't hindered, but hasn't been any help. So we had to do a bunch of work to integrate into VS Code and CLion, and Emacs and all the other myriad different IDEs that people use. One of the things
you
we
expect a full matrix. So like each and every one of the solutions will have its own set of support.
Exactly, yeah. But there is, unfortunately, no. That was when DAP first got announced, it was like, oh, great, maybe there's some. Now we can just everything will work with everything, but unfortunately, not at this level. No. So I've just got time, if there's no more questions, for my second soapbox.
Yes. This is why we print them.
Right, yeah. Now, actually, it's a lot less of a problem when you've got time travel because you can do a few reverse step I's and usually and often get back to when the value is live. So that's better, but what does it mean? Obviously, it's a trick question, but
the compiler didn't document correctly enough where the value were live.
Yeah, right. So it's kind of lying to you, right? It says value optimized out. Sometimes it has been. Sometimes that value just genuinely doesn't exist anywhere in the program. But usually that's not the case. Usually it is totally there. If you look at the disassembly, you can see it. And the compiler just hasn't generated the debug info to deal with it. Yeah, I mean, I think this is, it's kind of sad that the amount of effort that goes in to making the compilers generate just slightly better code, saving a few nanoseconds here or there, and the sort of the cost benefit of that is again, is the economics of this, right? So a lot of the people who are funding that development are people like, say, Google, who if they shave 0.1%, what the generated code is 0.1% more efficient, then they can save loads of money in their data center bills. Whereas the cost of all these value optimized outs is spread across a much wider number of people, but smaller amount each. So no one kind of has the incentive. If the compiler generates bad code, that's a bug, and people take that very seriously, and as they should. If the compiler generates bad debug info, well, it doesn't really matter, right? And I think, yeah. So on my soapbox, this is something I think that the world needs to fix. I think the economic benefits from just a small amount of work to make compilers do a better job at debug info would be significant. So if anyone's interested, I am trying to get together a little kind of little sort of group of people who are. I found there's some people at King's College London who are interested in addressing this problem, and I want to get a bunch of people who are feeling the pain to jointly fund that group at King's College to make this better, because it's not that hard. It doesn't take that much, but we just need to get together little little consortium of people who can put but who are so it could be larger companies who know that this is costing them in productivity every year some meaningful amount of money. Yeah.
Are there specific compilers that are notoriously good or bad in this?
There's some nice research. There's a paper by Stephen Kell and Ryan, I've forgotten his surname, from King's College London on this. For most of the things they looked at, they did quite an extensive study of the debug info that's generated by the different compilers at the different optimization levels. Most of the time, Clang is worse than GCC, interestingly, because it has a reputation. I've spoken to people who said they've switched to Clang because the debug info was better. But according to this research, well, I mean, it depends. It's all over the place. But on the whole, GCC does a better job. Clang doesn't even. So GCC has, at least GCC kind of has a bit of a go. They have this -OG optimization level, which so it does. If you go -0, then I mean it's really bad, right? Every single, it doesn't even try and cache anything in a register, or right. And -OG will do kind of a decent job and try not to still generate it. Clang does have a -OG, but that's just -0. It's not actually doesn't actually do anything. But there's not a massive difference between the two. They both have lots of room for improvement. But I think there's, how we get the culture change in that community, right? Bad debug info is a compiler bug.
And are there known problems or issues with like the debug info format, the dwarf format, which makes it impossible for compilers?
Yeah, so I think, so there's this sort of continuous race between like the clever and cleverer optimizations and then more and more expressive dwarf formats. But I'm not asking for the world here, right? I'm not saying it should be perfect. I understand there's going to be cases where you can't do this, but it could be, it really feels to me like there's a relatively small investment could make a big difference I think there's some low-hanging fruit, I really do. In the meantime, at least if you've got time travel, you can move around a little bit and find. We're actually we haven't done this yet, but we're going to do something I think that when we see value optimized out, automatically moves around up and back and forward a bit and sees if it can fish it out. So, who gets the mug? Who really wants the mug? Oh, Chris's hand went up first. You get the mug.
I didn't ask a question. I was actually going to say that you asked a really good question just then.
Who wants the mug? Yeah. Well, I can't judge on the question, so you were the keenest. And I didn't like set it up at the beginning, which I should have. So have a mug with x36 assembly on it.
Thank you.
Treat it carefully. We actually had somebody email the contact us thing on the web. When we get contact us on the website, like 90% of it's junk. Sometimes it's people who are really interested. Most of it's people trying to sell us stuff. Somebody recently said they had a mug. They had that mug from a conference and they'd broken it, and please could they buy another one? And I was like, you could buy some software. I'll give you a mug.
Does the software come with a free mug?
Sorry?
Does the software come with a free mug?
I mean, I will state here publicly, I will give a mug happily to anyone who wants to become a customer. Because I'm pretty sure I'll still make a profit on that.
Yeah, pretty sure.
Yeah, I think so. You got to think about this stuff. Bottle openers. 1, 2, 3. There we go.
Thank you.
Actually, I think they're bottle openers. I didn't actually check.
They have only
Yeah, it is. There you go. There you go. You can have the little. Yeah, they're quite nice.
Goes on your
Funky.
key ring.
Yeah.
Any interesting?
Wait, can you put the top back on the bottle with this?
Observation.
We've already exhausted the quota of time travel jokes.
Anything to note on the intersection between debugging and LLMs or AI?
Yes. That's a good. How long have we got? Just yeah, it's a good time. So, yeah, there's a number of things here. One is, what can you learn from the recordings? Right, the recordings have a lot of really interesting information in them, and yeah, so we're kind of looking at that right now. It's, probably the lowest hanging fruit here is, what can you do about comparing two recordings? So I've got my flaky test. Say, I've got 99 good executions and one bad one. Where did they diverge in the interesting place, right? So that's, and then you can keep going from that. And kind of what are the more, maybe this even looks like it's under some kind of security attack. It's like the behavior's now changed, or just this looks like probably this is usually buggy when this happens. So you probably want to look at that. The other thing that's interesting is, of course, there's a lot of stuff out there of LLMs diagnosing bugs for you and maybe even offering up solutions. And of course, this gave me a bit of pause for thought, right? What does this mean for the business in the long term? I've convinced myself that it's fine because two things are happening in parallel. One, the LLMs are kind of getting good at debugging, and you give them some simple problems and they can be quite impressive. More and more code is being generated by Copilot and other stuff like that that's going to look right, because these things are essentially plausibility engines and not quite be right. So depending on, like, that one's going to hurt business, this one's going to help business, and I'm sleeping okay. I think this one's going to help more than this one hurts. Yeah, but it's definitely interesting times. Yeah.
Like help meaning like there'll be more bugs to...
There'll be more really subtle bugs.
Okay,
yeah. Code that you just... The other thing actually, if we have time on, if we're talking about kind of future stuff, is Rust, right? And people say, well, Rust doesn't have any bugs, right? That's probably bad for business. I think Rust has 3 really good properties for meaning that the debugging is actually much, much easier in Rust code. One is the borrow checker, one is the type system, and the third is that there are no 10-year-old Rust projects that have been worked on by hundreds or thousands of people, and all the original people are like, let's wait until we're there. I think more broadly, back to my earlier slide with the Kernighan reference, debuggability becomes the limiting factor. So what will happen is
We'll be more ambitious.
We'll be more ambitious, right?
Yeah.
And you know, we will continue to write code until it doesn't work anymore, and then try to fix it.
And better tools means you could write more code.
Yes.
Everybody, my experience has been people write code up to the limits of their tools.
Yeah, right, absolutely. So double the debuggability, you double the goodness of your code, and tooling more generally, right? Yeah, I know. You know, one of the things, as I'm on my soapbox, that I hear sometimes still, debuggers make programmers lazy. Like, what does that even mean? Detractors make farmers lazy? Right, there's a kind of machismo thing going on, I think, sometimes. Yeah.
I believe there's some truth in that because it's easy to write a bunch of code, compile it, and run it on the hope that it will work.
Yeah.
And if it doesn't work, then you start debugging it.
Yeah.
As opposed to you write some code and you compile it, and then you sit there and look at it for a little while, see if there are any obvious bugs.
So, yes, but I think that's just about that's a kind of process thing, right? Because it doesn't matter if you're using printf or debuggers to, basically start with the empty file and debug, right?
But no, I was thinking more of what used to be called desk checking your program.
Yeah, yeah.
Back when it was expensive to run your program.
Yeah. No, it's
back before I started doing things. People used to write their programs and then they would sit down and work through a few samples at their desk before they tried running.
Yeah, absolutely. We actually, I've got an anecdote on that. So the first, when the company was very young, we struck a deal with ARM to port, make it work on ARM. So because we're JITting, it's a lot of work, right? And basically you have to take the instruction set manual and you start with add, and you go all the way through until you've done XOR, and you just have to support all the instructions. And we were working with a guy at the time, early on, a chap called Richard, who kind of taken early retirement and was looking for something fun to do. We didn't have any money to pay anybody, but he was happy to work on something interesting for shares. So he said, and I had this deal. So if we make this ARM version, then we can get a big check from ARM. For us at the time, was a significant check and was going to really get the company off the ground. So Richard starts, and we think it's like 6 months. Yeah, maybe 6, plus, give or take. 4 or 5 months in, how's it going? Yeah, I'm getting there. It's like, I'm up to, V or something in the instruction set manual. So progressing. So I went back to ARM. So it's going to be a little bit late, but we're making progress. Okay, a few more months. Yeah, I'm nearly there. Right, I've done most of the stuff now. Mind you, I haven't tried to compile it yet. And I thought, oh my God, the company's toast. I've got this whole deal hanging on this thing, and the guy's insane. He's done months of work and he hasn't even compiled it. And then he went, but yeah, I tried to compile it, didn't compile, but fixed that, didn't run, but fixed it, now it works.
Yeah.
Because he started writing on punch cards, and it's just different way of doing things. Yeah.
So most of the time I spend in the debugger is just walking through the code, working correctly, just to see how it's going.
Absolutely, right? And hence the Doom DAO. I wasn't debugging anything in Doom, right? I was just trying to understand how does this flow, got all this stuff and there's function pointers and, there's opaque bits of code and there's libraries being called, and like, how does the whole thing stick together? And customers generally, I say, they come for the bugs, they come for the debugging, but they stay for the just code understanding. Yeah. Oh, the other thing, just on debuggers and tools and lazy and not, I think it's true what you say, Marshall. Yeah, actually, that's a good point. There's another thing that is more significant, which is the kind of patch fix, right? So I don't really understand. I've got far enough to know, well, this thing's null, it shouldn't be null, but I'll just do a test for null and it stops my test failing. Right, done, bug is fixed, move on. And not really going back to the proper root cause. I fully understand what's going on now. And I think that's, obviously, we're all under pressure and everything. And so giving the tools to allow the developers to properly root cause understand the bug rather than just some effectively random change that now makes the test pass. It's got to be a good thing.
Yeah. Fixing the symptoms rather than bugs.
Yes. Yeah.
By the way, any work or thoughts about like visualizing recordings?
Yeah. So that's hard. So there's been a little bit of thought on it, not a whole bunch to be honest, because if I'm going to be really honest, I don't think we've had any good ideas yet.
Yeah, like it has to do with the fact that, as you mentioned, it's probably less about debugging and more about understanding, right?
So visualizing the code flow somehow.
Like which are the common?
It's a problem of scale. So you can do it. And there have been multiple instances of this. You build a kind of tree view of the function call, and you kind of go into that stops working when you get to like millions of lines of code, right? It just becomes it's great for kind of small things. You can make some nice demos, but it doesn't scale, and that's what we're interested in here is like the millions of lines of code scale problems. So I think there's something there. We haven't figured anything out, and I haven't seen anything out there where I've thought, yeah, that's the answer. But I believe it's there to be discovered.
I assume once you have a recording, you can add a printf to that recording and run.
Yes, you can. Yeah. So that's something we call post-failure logging, which I don't really like the name, but anyway, yeah. So you you can query. So I've showed all the demos, essentially demos in the debugger interface. But yeah, you can query what would it have looked like if only I had that printf there on this particular run, and we'll give you that. Yeah, and that's quite a nice interface. Yeah.
I was interviewed at a place where their business was patching running programs, patching programs while they're running to fix bugs in them. I can't remember what the company was, but I mean that's the sort of thing you could get into.
Yeah.
It's like kernel people do that, live patching.
What?
Live patching.
People with process systems. Process control systems.
Right.
You can't just bring the thing down and.
Right. You have a water treatment plant that's serving 100,000 people, and you need to.
Yeah, or the Voyager thing recently. Like I don't know what they did, but
Or the Voyager thing.
Yeah.
That's software engineering right there.
Yeah.
You got something that was launched in the 70s.
Yeah.
It's got what?
It's got two 1802 processors in it.
And what, 8K of RAM, or rad-hardened RAM.
Yeah.
So one of the big challenges with hot patching in modern software, though, is the idea of hot patching is, well, you can take function f and replace it with f prime, with another definition. But like a large part of modern C++ optimization is interprocedural optimization. It's where you optimize G in terms of f that it's calling, and so if you replace the definition, like maybe you've also affected G, and it becomes tricky.
And G or F has been half inlined.
Right. Yeah. Or you've removed code that was dead, and now it's not dead anymore because you've got different code data flow.
Yeah. I think we've digressed. I think probably that is the time to wrap. Thank you very much, everyone.